So up until now, we've been talking about using one single sample to draw conclusions about the population. This is occasionally used, but the majority of studies that we're going to talk about actually compare two or more samples. And so the t-test for independent samples starts allowing us to do this, and it's about the mean differences between two different groups. We've got some new statistical notation, and in particular, because we're dealing with two different samples, we're going to have two different sample means, two different standard deviations, one for each sample, and two different n's or number of participants in each sample. And so using two different groups allows participants to assess the effectiveness of two different treatments. So it allows researchers to evaluate the mean difference between two populations using two separate samples. So it's involving separate or independent samples and making a comparison between groups. The alternative, which we're not going to discuss in this chapter, is you could be doing a within subjects or repeated measures comparison where you have two different responses from the same people. But here it is two distinct groups, which is why we call it independent measures, or sometimes between subjects, because we're comparing different subjects. So the independent measures design is used in situations where a researcher does not know anything about either of the two populations or treatments being compared. So in particular, the population means and standard deviations are all unknown. And again, we're assuming that these two groups come from, or we're testing whether these two groups come from different populations. So examples are men versus women, or people who get a drug versus people who don't get a drug. The subject score is measured under two different conditions of the independent variable. And of course, this produces two means. One group is mean one, sample mean one, which represents population mean one, and the other group is sample mean two, which represents population mean two. So for example, maybe we're looking at the achievement scores for children taught by different methods. And we want to know, do kids in method B do better than kids in method A? So in statistical terms, we're basically assessing whether the two population means are the same or different. We don't know either of the two population means, so we're going to take two samples, one from each population. So sample A is going to provide us with information about population A, and sample B is going to provide us with information about population B. So as with all hypothesis tests, the general purpose of the independent measures t-test is to determine whether the sample mean difference obtained in our study indicates a real difference between the two populations, or whether the obtained difference is just the result of sampling or sampling error. Okay, so the hypothesis test provides this kind of standardized formal procedure to measure the mean difference between the two groups. Remember that if two samples are taken from the same population and given the same or given the same treatment, there'll be no difference between them. So again, the test is to figure out, is there a difference between the two populations? So anytime we look at this, we may have theoretically population 1 and population 2. So if they really are different, we could have a small difference of only 20 points or a big difference of 50 points. And if we select one score from each of these two populations, the closest they could be in this case would be 20 points and the farthest would be 50. So we're, again, just like with an independent samples t-test, with a one sample t-test, kind of looking at how likely is it that we would get the difference between the populations if there really were no difference. So the hypothesis test follows the same 4-step procedure that we've been looking at in chapters 8 and 9. So we're going to need to get sample means and sum of squares, or standard deviations or variance for each of our two samples, but generally, we're going to start by stating the hypothesis. We're going to locate our critical region. We're going to compute the test statistic, and we're going to make a decision. So just like with the other t-tests, I will give you the alpha level. You set the alpha level predetermined, most likely 0.05. For the independent measures test, the null hypothesis is that there is no difference between the population means. The preferred way is to kind of do this way. This is the way your book presents it. And so your hypothesis, your null hypothesis would be that mean 1 minus mean 2, and indicating the population mean, equals 0. Essentially what that means is they are the same. An alternative, and the alternative hypothesis would be mean 1 minus mean 2 does not equal 0. There is some difference. You could also do the sample means, and you could, or the population mean, and you could set these up so that they're equal. So you could say x1, x bar 1 equals x bar 2, or sample mean 1 equals sample mean 2 as the null hypothesis, and the alternate is that sample mean 1 does not equal sample mean 2. But again, the idea here is that the null hypothesis is there's no difference between the groups, and the alternate hypothesis is there is some difference. Okay, so the next step is locating the critical region. And we're still using our t-table from Appendix B2 to figure out where the critical region is. The big difference here is that we have 2 samples, so we need to calculate our degrees of freedom. So instead of just having n minus 1 as our degree of freedom, we actually have 2 different samples. So the way we do this is our degrees of samples, degrees of freedom for an independent measures t statistic is n1 minus 1 plus n2 minus 1. So we're taking each of the samples' degrees of freedom and adding them together, or n1 plus n2 minus 2. Okay, so we'll go and look it up in our table and determine based on the degrees of freedom, select the alpha level, and figure out what our critical value is for the criterion region. Okay, the next step is to compute the t-statistic. And the t-statistic for an independent measures design has the same basic structure as the one we introduced last chapter. But in this case, all components of the t formula are doubled. There are 2 sample means, there are 2 population means, 2 sources of error contributing to our standard error in the denominator. So we'll go over how to do each of these steps, but I wanted to kind of have them written down for you so you can refer back to them. If you're given 2 independent data sets and need to calculate an independent samples t-test, these are the steps that you need to take. There's a lot of calculating you might need to do. So again, this is just kind of a list of the steps, and we'll go through each one. So calculate the mean n and degrees of freedom for each group. So you need to have those. You need to find the sum of squares for each group. You need to calculate the pooled variance. I'll talk about how to do that in a moment. So we can't just have the separate variances. We need to pool them. You need to calculate the estimated standard error and then compute your actual t-statistic. Okay, so this table just kind of does a nice job showing the parallels between a single sample t-test and an independent sample t-test. And the basic elements are the same. But it gets a little more complex when you're dealing with your independent measures t-test because we're dealing with 2 groups and we have to think about how to compare them. So we are comparing, instead of just having 1 mean, we're comparing 2 means. But we're making hypotheses about the difference between the 2 population means. And now, instead of just having 1 standard error, we have to actually pool the standard error from 2 different groups and use a pooled sample variance. Okay, so the formula, these are the formulas for computing the independent samples t-test. We're kind of working our way backwards. Remember that the t-test is the sample mean minus the population mean divided by the standard error, right? So at a basic level, t is the sample mean minus the population mean divided by a standard error. When we're comparing 2 groups, we want to be able to extrapolate about the 2 population means. So here we're looking at the sample mean difference divided by the standard error. Okay, so in order to estimate the standard error of the mean difference, which is essentially telling us how accurately the sample statistic represents the population, we've got 2 different populations, so we've got 2 potential sources of error. So in a single sample, the standard error is the amount of error expected for the sample mean. In the independent samples, we're looking at the expected error when using a sample mean difference to represent the difference in the population. So this is the standard error of X1 or M1 minus M2, right? Of the first sample mean minus the second sample mean. Note this whole thing should be under the square root. So this entire thing is in the square root. So the standard error of the mean for an independent samples test measures the standard error of the distance between mean 1 and mean 2. Okay, so we're looking at the standard error of the mean difference. When we're comparing two groups, we want to know what's the variability around the difference of those two groups. So you'll see that this requires an SP2 is the pooled variance. Okay, so the pooled variance happens because we've got two different samples that may have different sizes. And so instead of, so we need to pool the variance because the pool variance is essentially a weighted average of the two variances, where the bigger sample gets more weight. Okay, so it's essentially, you can think of it as a weighted average. And to get the pooled variance, you add the sum of squares for sample 1 to the sum of squares for sample 2, divide that by the degrees of freedom for sample 1 over the degrees of freedom of sample 2. In order to get that, you need the sum of squares for each group. And so remember, we've got this formula for calculating the sum of squares. So you can go through and do the way we did when we learned the standard deviation, and go through, take the, you've got each individual score, subtract the mean from each score, square it, and then add it together to get the sum of squares. Or I gave you this computational formula, which is sometimes a little bit easier to use, especially if you have big samples. So the sum of squares is the sum of x squared. So remember that you need to think about your order of operation here. In this case, you're going to square each x and then add them together, minus the sum of x squared. So here we've got parentheses, so you're going to do this part first. So you add all your x's together and then square that number divided by n, and you do this for each group. Okay, so essentially you have to work your way backwards. First, you have to get the sum of squares, then you get the pooled variance, then you get the standard error of the mean difference, and then you can calculate your t-value, which brings us to this list right here. Okay, so you do that, you calculate your t-value. Your next step is to make a decision. So again, this is just like you did with the single sample t-test. If the t-statistic indicates that the obtained difference between the sample means is bigger than the denominator, than that expected by chance, we reject the null hypothesis and conclude. So remember here, the null hypothesis is that there's no difference between the means. So if we reject the null hypothesis, we conclude that there is a real mean difference in the population means. If you don't reject the null hypothesis or fail to reject the null hypothesis, we conclude there is no difference. We can also do a one-tailed test if you have a specific directional hypothesis, okay? So if you expect your first mean to be larger than your second mean, this is what your hypotheses would look like. And again, the null hypothesis is still no difference, but your alternate hypothesis changes a bit. Again, it would change depending on the direction. And of course, you need to be sure to select the one-tailed value when you're finding the critical region for the independent samples t-test. Sorry, for a one-tailed t-test. Okay, so there's a couple of assumptions associated with the independent samples t-test. The first is that we need to be measuring interval or ratio scores. The next is that the population of raw scores is relatively normally distributed. So generally, we're dealing with normally distributed data. We also assume that the population from which the samples are selected have equal variance. So this is called homogeneity of variance. And we're assuming that our treatment and our non-treatment groups still have roughly the same variability in them. Okay, so this is an important assumption. Most hypothesis tests work really reasonably well, even if the underlying assumptions are violated, but the homogeneity of variance one is kind of an exception. Okay, so you really need to have this homogeneity of variance in order to justify pooling the two sample variances. Okay, so this is really becomes an issue mostly when you have two samples of very different sizes. But the way we test this is a test called Hartley's F-max test. And it's a null hypothesis test. And with this, the null hypothesis in this test is that the variances are equal. So the null hypothesis in this test is that the sample variances are very similar. For this case, we're actually hoping that we fail to reject the null hypothesis. We want to assume that the variances are equal and that it didn't violate the homogeneity of variance assumption. If you reject the hypothesis for the F-max test, it's saying that your variances are unequal and maybe you shouldn't use the t statistic, or you need to be careful or use a different variation in that. And when we get to SPSS results, I'll show you kind of where we get that information. Okay, finally, we'll talk in class about a little more about different measures of effect size, but one of them is using a confidence interval. So we use the confidence interval in roughly the same way that we did a single sample t-test. We're mostly looking at a 95% confidence interval, and it's a way of measuring effect sizes. But with the two samples or the independent samples t-test, we are looking not at the confidence interval around the actual mean, but the confidence interval around the difference between the two means. So how big or small might this difference be? So we calculate it by adding and subtracting the product of the t-values times the standard error of the mean difference from the sample means, which gives us a range of t-values. So we've got mean 1 minus mean 2, because it's all about that difference, plus or minus your t times the standard error of the mean difference. So we'll go over lots of examples of how this actually works in class.